cluster approach. It's called K and it's called means because it is a center-based method and it uses a centroid. Centroid was the mean of all the points, remember that? So the K-means is going to use the centroid, or it's going to take the average or the mean of all the points in the cluster, and then we'll compute the distance from each point to the center. And there is more than one center. In fact, there is exactly K centers, and that's why it's called K-means, because we have K number of centers. So each point will be compute the distance to each of the centers that we have, and whichever center the point is closest to, it will be assigned into that cluster. So the number of clusters is K, and this is specified by the user or it's predetermined. In other words, before we start this algorithm, we need to know the number of clusters K, and we can ask the user, how many clusters do you want to have? And let's say they will answer and say, I want to have 3. So if you want to have 3, then it will be 3 centers. We can choose them by random and start computing the distance from each point to each of the 3 centers. And whichever one is closest to, we will put the point into that cluster. So select K points as the initial centroid. Like I said, that could be at random. After we've done this, we will repeat what? Form K clusters by assigning all points to the closest centroid. So we compute the distance to all the centroids, whichever one is the closest, assign the point in there. Once we have done this for all the points, guess what? The centers will change, right? Because let's say we started with this center and that point was in here, but now we added this point and a couple of others. And now we have a cluster of 25 points. Is the center still gonna be here or it's gonna go somewhere else? It's gonna move because we're gonna take the average. So we need to recompute, after we're done with all the points, we need to recompute the new centers. And repeat until once we recompute them, they stay the same. If that happens, then we are done with this algorithm, and we have the optimal clusters. So we can have many iterations until that happens, or maybe it will never happen, but we come very close to it and we will stop. So we can have a number of iterations until we converge with this algorithm. So let's see how it looks like once we start doing that. Now the distance that we're using, Euclidean is the most intuitive distance which you probably think about. But there are other distances, as I mentioned, that can be used, like cosine similarity, correlation, Manhattan distance, or some other function that we want to specify, that we like. And say, this is going to be our function point to calculate the distances. And again, it will converge once the centers no longer change, or we come very close to where they're not changing anymore. So if we start with a bunch of points and we have chosen the centers by random, exactly points were chosen at random as the beginning of the clustering. So we could end up with something like this. This is cluster 1, cluster 2, and cluster 3. Or it could happen that these 2 points now belong to that cluster because they're kind of close to it. Or it could happen that the third cluster is everything that is in the bottom, and this whole piece up here was split into 2. It makes really a difference about these random points, which ones happen to be chosen in the beginning. But there's nothing we can do. We're just choosing by random.
One question. Is it important to define to which cluster belongs those random points, or they can be left outside of any cluster?
Okay. When we start, the points are actual real points. We just choose 1, 2, 3, because we have 3 in this case, are random objects from our data. So they are not outside of, they are actual real data points that are on the picture. They're not outside of the picture somewhere. So one of these actual real data points is chosen as the center. Let's say this one was chosen, this one was chosen, this one was chosen.
Right. What I mean, for example, the one in the green that is